All right, let's go to page 63 in your workbook. Halfway down where it says intercepts, minimums, maximums, and limits. And let's continue our discussion from yesterday about how to do this well. So first of all, I think we talked again about cover-up method. That's a good thing to use if it's set up in linear standard form, which is what we have here, x and y on the same side. And then you can get out your finger and you can cover up the 3y right here and just kind of do the work of division, which would give you an x-intercept of, well, if you divide by 2, that would be 6. So 6 for the x, y is 0, y is nothing when you cover it up. Go to the 2x and cover that up. It's gone. You have negative 3y, divide both sides by negative 3. Y is negative 4, so 0, comma, negative 4. Go ahead and put both points on the coordinate plane. And 6, 0. 6. And you draw your line, you got yourself a function on the graph. Sweet. Now let's run through the list of the new ideas that we've been discussing in this unit for functions. Relative maximum, relative minimum. Well, max and min occur at peaks and valleys. So there is no relative max, there is no relative min because there's no highest point, lowest point in terms of a peak or a valley. Global max and global min, again, same thing. They have to occur at peaks and valleys. So none of this is actually present. But what we can do is talk about limits and where is the function going as, remember, decipher this. The limit as x approaches infinity, what I see there, of the function. So if you want to put f of x right there, that stands for function, is equal to, well, as you travel to the right on this function, so as you're moving this direction over here, like that, the function is increasing in value. So as you go to the right, my traffic cop says go this way, the function is going increasing towards infinity. So there really isn't a limit there. The limit is infinity, which means it has no limit, essentially. And then what is the limit as x approaches negative infinity of this function that is linear? Well, as you go to the left, or as x goes towards negative infinity, the function is decreasing forever. So it's going towards negative infinity. Remember, think about direction in the x, and then in the y, where is it headed? Is it converging, diverging? Okay, those are important things to discover or discuss. Hiya! Sorry, I made some mistakes on the second example on page 63. Don't have time to go back and fix those right now. So turn to page 64, and let's look at average rate of change in terms of world population. So please go there. Simple questions. Find the average rate of change, which we know is the slope, from 1925 to 1975. So in 1925, there were 2 billion people approximately on the planet. And in 1975, there were approximately 4 billion people. So if you just do the rate of change, let's know that we're working with billions. So I'm just going to do 4 minus 2, which is y minus y, over the time frame, which is 1975 minus 1925. That's 2 billion people in 50 years. Okay. So knowing that we're working in billions, if I were to divide that out, of course, that's 0.04. But that's not 0.04. That would be 40 million per year. Whoa. That's a lot. That's crazy. 40 million per year. People per year. Dang. Well, that's for the world. So on average, over those 50 years, we added 40 million people each year. Impressive. Let's take it a step further. Go from 1925, we're 2 billion, all the way up to the year 2000, where we had 6 billion people. So 6 minus 2 over 2000 minus 1925. That's 4 over 75. Divide those two. Now I'm getting 0.053. If you move that decimal, okay, like you know you're working in billions, okay? So that would be 100 billion, and then you're talking about 10 million. So that's 53 million. 333,333 people per year. approximation anyway. So slightly more. So over a 75-year period, we added 53 million people per year. As you can see, the graph is not linear. There's this gentle little curve here. And it kind of does this, like, it kind of goes up and it's going to trend back down. We see this a lot in population graphs. There's steady gains, and then there's exponential growth, and then it starts to level out due to constraints in terms of land mass, resources, those kinds of things. That's going to limit what happens with global population, regional population in terms of countries, and so on. And that's a pretty typical graph for population. All right, let's do one more. 100-year span, so from 1925 to 2025, which we haven't eclipsed yet, but this was a projection, this map was a projection of a couple of years ago. I just saw on the news recently, within the last year, that we have eclipsed 8 billion people already in 2023. This is projecting for 2025, so as you can see, we're still approximating. Well, let's say in 2025, there's still 8 billion some people on the planet. We haven't gotten to 9 yet. Let's go ahead and make the slope of that with a rate, 8 minus 2 over 2025 minus 1925, which of course is 6 over 100. And that is 60 million people per year. And as you can see, the trend is, as we go from our starting point, which is 1925, and we draw consecutive slopes between 1975, 2000, and 2025, the steepness of that slope increases slightly every single time we do it, okay? We're approximating that in the year 2050, we will have close to 9.5, 10 billion people. And I've heard projections of a stabilizing number of like 11 billion. They would forecast that we'd get to about 11 billion as a planet, and then due to constraints, that number might start to level out and possibly drop, we'll see. Okay, write a function for the average rate of change from 1925 to 2025, okay? Well, that would be y equals the rate that we came up with, which is 60 million per year, times x, plus our starting value, which was 2 billion. I'm actually gonna write that number out, why not? Have some fun with it. Look at all those zeros. It's glorious. Okay. And now, can you use that function to predict the world population in the year 2050? I said based on the graph, it would be about, what, 9.5 billion? Does that hold true? Okay, so do the work. What are you going to input into the calculator though? You're not going to put 2050 in there. 1925 is your 0 mark. So if you go 1925 to 2050, that's what? 125 years, okay? So that's what you want to input in for x. So y equals your 60 million per year times 125 years of growth plus the starting value of 2 billion. All right, here we go. Yeah, 9.5? 9.5 billion people. Okay, that's not that long from now. We'll get there. See how it goes. All right, my last example is a cylinder. We've done one of these already. I want to show you again a process by which we can get a function that we can plug into to maximize some things or minimize the others. In this case, we want to minimize. It says the cylinder has a volume of 50 cubic centimeters, so it holds 50 cubic centimeters of liquid or whatever. And you want to find the value of the radius that would minimize the surface area. So we want the smallest container possible that still holds this amount of liquid. Well, there's two different formulas in play here. So last time we started with the volume. So on this side, start with V equals pi r squared times height. Remember that? It's the area of the base, circle, times h.
Base, height.
Okay, here we go. And then on this side, we're doing the surface area. So we're going to cover this thing with paint, wrapping paper, whatever it's called, and find the surface, the area of the surface. So that would be, follow me, 2 2 pi r squared, or also known as 2 circles, plus 2 pi r h. And notice that 2 pi r is the circumference, which is the distance around the circle, times the height. That's how you find the area of that lateral face right there. Okay. We're going to solve for one, plug into the other. Here we go. Volume. We know the volume is 50. I'm just going to plug that in. 50 goes right here. In for V. Okay. And now remember, H is the one that we're going to solve for. So I'm going to put a little note around H and say, I'm going to solve for you. Everything else must go. So fire sale, here we go. Divide everything by pi r squared, get that out. And now H is going to be by itself. Remember, these cancel from this side. And it's equal to 50 over pi r squared. And now we're going to send this thing packing. We're going to put it in a box. So take 50 over pi r squared, which is equal to H. And you're going to ship it, FedEx style, over there in for H. This is messy, but it's attainable. It's okay. It's just messy. All right, follow me. Surface area equals 2 pi r squared plus 2 pi r. And when you hit H, that's when you want to plug in the package that you delivered, the 50 over pi r squared. So in parentheses, put 50 over pi r squared. And now we're going to do a little cleanup, okay? Because, yeah, this is okay, but it's definitely messy. You might notice that there's a pi right here and a pi right there. You can cancel those because they're above each other in terms of a fraction. You can put this over 1 if that helps. So cancel the pi's. You can cancel this r with one of those because there's r squared, there's 2, leaving 1 in the denominator. And then the last thing is you can take the 2 times the 50. Okay, so let's do all 3 of those. Surface area equals 2 pi r squared plus 2 times 50 is 100. Pi's cancel. This r cancels with one of these, leaving 1 on the bottom. Oh, it's beautiful. You might remember that at this moment we said, what kind of function are we dealing with at this moment right now? Well, it is quadratic because of the r squared, but it's also rational because it has an r in the denominator. So it's this hybrid of 2 functions. And when you put it in Desmos, you will see the craziness of, it looks like a quadratic, it has this vertical asymptote, this place where we can't go, and it's kind of all over the place. But in the positive realm, quadrant 1, there is a minimum. So what I need you to do right now is get out your computer and type in this equation, substituting y for surface area, so y equals, and then I need you to change r to x, because Desmos would read that a little bit better. So 2 pi, type pi, the pi symbol will show up, x squared plus 100 over x. And what you're looking for is the minimum value in quadrant 1. Click on it, Desmos will make it appear, write down the coordinate right there, and identify what the coordinate means. What is the x part of the coordinate? What is the y part of the coordinate? What are we looking for? We're looking for minimum surface area. Okay. So I trust that you'll do that. Then you're going to go to the website and complete the activity after the video, and hopefully get that done and have time to do AI. Let's see. Okay. So good luck. I'll see you guys later.